Hi everyone, this is going to be our note for 6.2, sinusoidal functions and periodic behavior. So we're going to interpret graphs that repeat at regular intervals. So you might be wondering, where's the 6.1 note? Well, the 6.1 note is kind of periodic behavior, and it just goes over this idea. It's a very short section, it's kind of an investigation, where the idea is this term periodic. It means happening or appearing at regular intervals, or having repeated cycles. So there are many examples of periodic behavior. The one that we kind of did in grade 9 when we were doing EQAO stuff is we had these things called these distance time graphs, where we had these graphs here. And we said that this is the person's home, or I think they might have said there was like a sensor, but we'll use the sensor. It was here. And if I had to draw a picture of this, is like we had a sensor here on a table. And then a person would stand here, and then they would walk away from the sensor, and then they would walk back towards the sensor. And if this was the sensor here, this was time, and this was the distance, and the distance was how far away the person was from the sensor. So if they started at the sensor, and as time went on, their distance would increase from the sensor, and then eventually they would come back towards the sensor. And if they kept going back and forth like this, you could see this cycle occurring, where they're just going back and forth, and we could kind of assume what's going to be happening as time went on. They would just keep going back and forth, and this pattern would be repeated. So this is what we call periodic behavior. If you wanted another example, we could think of high tide and low tide with water elevation. So like if we have like a beachy area, another beachy area, about every 12 hours, the water levels change. So it might be really high up here, and then later in the day, it might be down here. So it might start up here as a water level, and then down here due to the tide. So if we were to graph this as well, we could see that the water levels would maybe start off higher this time and then go lower and then high again every 12 hours. So we can say that this is also exhibiting periodic behavior. Oh, you'd like another example? All right, well, more examples. Let's say we have like a car, and then what do you have on the car? You have usually a wheel. So let's say this is a car wheel, and we have the ground here. Car's driving along on the ground. If I were to put a point on this wheel, let's say a point here at the base of the wheel, and then I were to track the distance this point is from the ground. Well, I could make a graph of that too. Here's the ground. And right now, again, we're doing time. This is distance from the ground. And we might start here because it's touching the ground, and then as the wheel moves and spins up here, it's going to increase in distance away from that point. It'll then get to a maximum point where it's the farthest away from the ground, and then it'll get back closer and closer to the ground again until it's at its original point. And then this would continue the cycle as the wheel turns, the distance away increases and decreases again. And the cycle will keep repeating as long as that wheel keeps moving. So you may be wondering, well, why do we need to know this? Well, what if you're designing the tire? What if you're trying to figure out, well, how many, you can use this as a form of measurement, how many wheel turns before a person would have to replace the tire? Or you could think of how many wheel turns occur in maybe 1 kilometer, 10 kilometers. And they can use that measurement to say, to relate to somebody else, maybe a mechanic or people who are selling the tires. After this many kilometers or wheel turns, this is when you should replace the tire. So there's a lot of information that we can get from this periodic behavior. So I do have one more for you, because I know you all want one more periodic behavior example. It looks like this. So I have a little code at the bottom. Can you figure out what the code is? So this isn't really math related, but sometimes you get riddles or you get quiz, like little fun quizzes or little puzzles, and they'll give you these letters or this letters in this order. These just represent the months of the year. So like January, February, March, April, May, blah, 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 all the other months. They're all important, I just don't want to write all of them. So if we're looking at months of the year, and let's say we looked at temperature. Now if we were to record the temperature at different months during the year, well, we would kind of expect that maybe, in January it's going to be below 0. I'm not going to put any numbers in here because we're just going to show a pattern. Let's say it gets a little bit warmer, and then it gets hotter, and then as it gets, back to fall again, it's going to decrease in temperature. So winter months it's colder, below 0. Then as we get to like April and May, this isn't accurate because it's not 0 degrees in April and May, but please bear with me. But the temperature will go up, and then it'll go back down again. Okay, so I tried to make this look a little bit better. It's not that much better though. But we see the same idea of it's colder in the winter, gets hotter in the summer, and then when it gets to winter again, it gets colder. So this cycle can continue. And you might be saying, well, the temperatures aren't always the same temperatures every year. That's true, but we can kind of use this as a baseline for us to compare other things, to maybe make predictions about, temperatures for the future, or compare them to the past maybe. So the idea of periodic behavior can still help us in a sense. So now that we understand the idea of what periodic behavior is, when we have a pattern that's just repeating in cycles, we have different names for these parts of this graph. So let's go over the terminology. So first off, we have periodic, which we just learned. It's happening or appearing at regular intervals. Here we have a graph of periodic behavior. If we graphed it, it could be distance or various other things. Now, because it's going to be repeating over and over again, we have the peak, which is going to be the highest part on the graph, and the trough, which is going to be the lowest part of the graph. A period refers to the interval of the independent variable, often time, needed for repeating actions to complete one cycle, which, as I butchered that reading, just means how often is it for the pattern to occur and then start again. So like in this example, the pattern starts here, it goes up, it goes down, and then at this point, it's going to start again, going up and going down. So like on this graph, even though it's not drawn very accurately, my graph starts here. Well, when is it going to start here again, going up and then down again? What's going to happen? Here, up and then down, and then up again. So then this pattern would keep repeating over and over and over again. So this would be considered one period. Now a cycle is a series of events that are regularly repeated, a complete set of changes starting from one point and returning to the same point in the same way. So we can also say that this is one cycle. Just like in the wheel turning, one cycle was for it to get back to where it started from. So for this to go back to where it started from to repeat again, we can also say as a cycle. Now you might be wondering, well, what's the difference between a period and a cycle if they both just represent just one set of the pattern? The period is specific to the independent variable. So the period here refers to, well, what if this is time on the x-axis? Well, how long does it take for that cycle to occur? Well, the cycle is just, I guess, the cycle itself. The period refers to time, or whatever the independent variable is, for this cycle to occur. This next part just goes over what we did before about distance time graphs and some parts about the graph. So like what is considered periodic. And when we had no motion, it was linear. We have peaks and troughs, and the slope of a line would tell us the steepness for these line segments, which would also be the speed here. So just we've seen these kind of things before, and you can read over this if you just want to review distance time graphs. But another example of periodic behavior, this was in your textbook, is with phases of the moon. So the table shows the proportion of the moon that is visible from southern Ontario on days 1 to 74 in the year 2006. Well, how can we read this? Well, if this is just a proportion of the moon that is visible, we can kind of think of it like a percentage, where seeing all of the moon is 1.00 or 100%, and the less we can see would be, well, like something like 0. So here we can see very little, we see a little bit more, we see about half, and as the days carry on, we can see more of the moon till we get to here, then we see less, and you can see the cycle repeating again and again. Now, if we wanted to make a graph of this as well, it would look like this, which is also in your textbook. So if we look at the different parts of this graph, we have point 1 here. And this graph has the repeating pattern. Its period is 30 days. We can tell this because the proportion returns to 0 at 30 days. So our graph started at the bottom here, and then it started at the bottom again here at 30 days. This person used a repeating pattern to extend the graph to 150 days, meaning if they knew the pattern for the first cycle here, well, they can just repeat this every 30 days until they get to here. And then by predicting what the graph is going to look like, they can estimate how much of the moon is going to be showing at this day. So going all the way back to grade 9, again, we're doing some interpolating, some extrapolating, but now we can kind of extend our data because we know it's going to be in a cyclical fashion, or like exhibiting periodic behavior. So we have a question at the bottom that says, why does it make sense to call the graph of the moon data a periodic function? We can say because the phases of the moon occur in a regular repeating cycle of 30 days. Our next example just has us going over. Let's fill out this information we know based on the graph of this machine exhibiting periodic behavior. So I don't know if you've seen these like chopping machines. You push down on it and then it chops your vegetables for you. Well, here's the motion of that chopping machine. So what is one period in this case? Well, it starts at the top here, meaning nothing's happening, and then it chops, and then it goes up again, and then it starts here again. So this keeps happening, it seems like, every 2 seconds. Every 2 seconds, the cycle repeats again. So the period is 2 seconds. Now it says, what is the maximum height? Well, how high up does the machine go? Well, that's just the topmost part. It's not going to go any higher than this point, which is 2 centimeters. And then what is the minimum height of the machine? Well, what's the lowest point this machine goes for in this cycle? It doesn't go below 0 centimeters. So we can think of these maximum and minimum points. We can think of this as again a peak. It's the top part of our cycle. We can think of this as a trough, which is the lowest point. So what is the meaning of the flat sections here that's happening? What is happening to our chopping machine when it's flat like that? Well, it must mean when the machine, or the blades in the machine, is at rest. It's not moving. Just like in our distance time graph. So we saw a horizontal line. It means that the person isn't moving. So in this case, the machine is not moving. And what is the meaning of the V shapes on the graph? Well, this is the one the actual blade is actually chopping. So let's say the machine is chopping. So in summary, a periodic function is a function whose values are repeated at equal intervals of the independent variable. So what are some other examples? There's a whole bunch. You could probably think of a couple. I'll give you a couple. There's heartbeat. It's periodic. Inner workings of a clock. You might see on like grandfather clocks they have like a pendulum that goes back and forth, like a grandfather clock. Things like metronomes as well. Certain sound waves, like an ambulance siren, is periodic, kind of repeating back and forth. So there's some examples. So here's some homework as well, and thanks so much for your time.